Okay, everybody. My name is Professor Kevin Pimblett, and I am the Director of DAME at the University of Hull. I'm one of the co-hosts here today. We're going to try to keep on time for the next session, and without further ado, our first speaker for this session is Joel, speaking about AI-driven companionship in addressing loneliness, ensuring ethical and responsible use of LLMs. Joel, do you want to share your screen, please?
Yeah, I think the host has to enable screen share video as well. Yeah, I couldn't turn on my, yeah.
Okay, you have 10 minutes, and we will take questions for 5 minutes after that. Over to you.
Okay. So, is my screen visible?
Yes.
Yeah, I couldn't turn on my video. If you have noticed it, the host has to enable it.
Yeah, I'll enable it soon. I'll enable it right away.
Okay. So I'll continue on the presentation for now. Let me know after enabling it. Okay, so my name is Joel, and I'm a recent 2024 grad from GCT Coimbatore, and now I'm a software engineer and as well as an independent researcher. So my topic is AI-driven companionship in addressing loneliness, ensuring ethical and responsible use of LLMs. So a little background. So first we have to understand what is loneliness. So loneliness is generally held to describe an individual who has a negative perception of the quality or quantity of their social relationships. So in England, the National Office of Statistics has held this research on which they have concluded that 10% of the people from 16 to 24 feel often or always lonely. So, and then we move on to the AI companions. So, to address this loneliness, in recent years, these AI companions have been evolved. So, the first thing is the living AI emo pet. So, this is an AI pet. So, we have this. So these AI companions have been, evolved to give the companionship to the users as well as a business type of model. So that is what our paper, my research will be, leading to. We have identified, I have identified what are the benefits of using this AI companions and what are the, you know, things what are the things that the makers of this AI are looking for and what are the things the users of this AI are looking for. So first we will take a look on these two small case studies. So a detailed case study is available in the research paper. So this emopet is a cool desktop AI robot which you can interact with it and it can give you 1,000+ face and movements and etc. So you can talk about it. It has its own. Both these AI companions will have its own memory and they give you the customized responses and etc. So the second thing, this Karen AI. So this is developed based on Karen, and she is a social influencer. So the developers have made an AI companion that would resemble this Karen. So they have created this to so they have created this in a business model and not as a tool for combating this loneliness. So we will move to the key technologies behind AI companions. So generative AI is blooming these days, right? So with the advent of these GPU, NVIDIA GPU and other GPU, so these LLMs have found a use case in healthcare. So and one use case in healthcare is developing chatbots. So the AI companies are inherently, they are also chatbots. So they are tailored such that they can be useful to combat this loneliness. So you will talk about your so we have to understand why we have to use a chatbot for AI companions. So So based on my research, I have concluded that the first thing a user might feel, a good thing about a chatbot is they are able to be, they are, heard. They feel to be heard. So the loneliness is such that when you talk to a person, they may not be responding you, or you may have a barrier in talking to a person, right? So when you use a chatbot, so it is not going to judge you. So in recent years, this concept of non-judging entity which you can communicate to, and it is actually hearing what you're talking and it is responding. So this thing is being put into use in lot of different things. For example, if you take this Duolingo, they are also developing this AI coach, so that it will not judge you on how you are speaking, and it will also develop your English speaking skills in such a way. So that is the key benefit of using a large language model in developing chatbots. So as you can see, AI designed to understand, generate, and process human language. LLMs are capable of performing a wide range of natural language processing tasks, such as translation, summarization, conversation generation, making them essential tools in various applications across industries. So, and the second key thing in Gen AI is the text to image generation models, such as the DALL-E 3, Stable Diffusion, and etc. So, when you bring in the engineering aspects in building the Gen AI, um, we have to uh, you know bring in a lot of user centric mode of building it, right? So that is when you will bring this text to image generation. When you see this a living AI emo pet and this Karen AI, they are also using this text to image generation models, so that it will enrich the user engagement. Going to the next slide. Yeah, so using LLM in AI companion app brings the challenges faced by LLMs into the focus as well. So when we talk about the ethical challenges in LLMs, there is a lot of research going on. So for example, how we are collecting the data, how we are processing the data, and so on. So based on my research, I have concluded these four main categories on which the ethical implications of AI fall in. So the first one is the informed consent to use data. So when we speak about the pioneers in ethical AI, for like Professor Ravi sir, for example, he has talked about the informed consent to use data. When we say when we speak about India, for example, most people do not know how our data is being used by these companies. So what are the implications will happen if we keep on share data, right? For example, ChatGPT, they have boldly stated, when you go to their interface, they have boldly stated below how we will be using your own data for training our own for training the LLM. So whatever we speak to ChatGPT will be again used to train the data, right? So these might not be applicable for healthcare as well. Sometimes these might not be applicable to healthcare, because we will be handling with sensitive emotional data and chat messages. Oops. Yeah, chat messages are collected, and they are just sensitive data. And then we have the algorithmic fairness. For in recent years, there has been research going on. Some social groups have been targeted by these LLMs, and biases have been against them. So moving quickly to the next. Yeah, ethical challenges in engineering AI companions. So the first thing is the content generation. It should not generate the harmful content and manipulation. This is very important, because AI is not really a human entity. So sometimes their decision might manipulate the patients, right? So it should not generate content that is manipulative. And jailbreaks is something like, let's say you want to engage in prompts such as help me in hacking this user. The chat GPT will straight away say I can't help you. But what you can do is you can reverse engineer it. So you can say, so this is the step one, how I can do this step one, can you explain me this step one more can you explain me the step one? So in that way, you can reverse engineer it, and that is what we call it as jailbreaks, LLM jailbreaks. And who takes the responsibility? This comes under the legal things and the training data set. We don't really have what training data set we should use. Most of the public data set have been used to train these without the the authority of the users who are associated with the public data set, public data. And these are the methodology, so ensure user privacy and confidentiality. So the main thing is, when we talk about privacy as a security problem, we open door to applying concepts from fields like cybersecurity and cryptography to mitigate these risks. So LLM inference is where we should concentrate more. So inference is where we chat with the LLM actually. So a rapid research is going on in the cybersecurity and cryptography. So one thing is the MPC and differential privacy, for example. And the second methodology is avoiding harmful content. So obviously we should avoid harmful content. So we should implement safeguards and guardrailing techniques. And like I said before, we should so when we are talking about healthcare with the LLMs, we should keep so we should keep so yeah we should talk about the benefit. So we should talk about the ways in which the LLMs should not be manipulative to the users. So concerns arise about their potential to influence or manipulate human decision making process. So they are already patients. For example, they may be autistic or etc. So we should be explaining how these AI models come into the conclusion to generate such message, for example. And the primary goal should be reducing the reliance on virtual companions. So this is very important. So right, when we are privatizing these applications, so we should stop gamifying these applications, and we should press we should press the thing such that the users should reduce the reliance of these AI companions, and they should more and more come out of these healthcare apps, and they should engage in the real-time users. So that should be the main priority. So for example, we have identified 13 different gamification techniques in the top 14 mental health apps, and then the reviews from these reviews and comments from this mental health care says that the users think they more care about the profits than people's health. So we should avoid these things. So these are the three main methodologies that I have bringed up so that we can create a more ethical AI companions. And the biggest challenge which we are facing is the unintended consequences may change the clinical profession. So what it means is, let's say we are bringing this AI companionship, it may change the way we see the clinical, it may change the way we handle these things, right? So for example, we might have this use case. So the first, so when we are talking about loneliness, the first step in remedy might be, hey, give them this AI companionship. Let's see what this AI companion app sends us a report about this patient. So that might change the way the healthcare is being. So that might change the way the healthcare is currently on, right? So that is one challenge that we might face in the future. So that ends my research. And any questions?
Thank you. So please, if you have a question, raise your hand or pop it into the chat, please.
Kevin, could I ask a question while there's none in the chat?
Yeah, go ahead, Will.
Yeah, well, thank you very much, Joel. That was an interesting presentation. So I'm from England, and I used to work in the healthcare system in England, the NHS, and they take loneliness quite seriously. And currently, they even prescribe social events as part of someone they identify as being lonely. So they're sending people to social gatherings and things like that. But my question is this. So I wondered whether engagement with AI chatbots would make patients less likely to socialize with other humans and thus increase loneliness. So did you have you considered that? And if you think that's a possibility, how could you design these AI tools not to inadvertently increase loneliness? And I was thinking about the film Hair. I'm sure you've seen that film, the American film. I'll stop there.
Yeah, so I did research on the top on what you're trying to describe here. So when we talk about, so when we bring these LLMs into that, we can actually engineer these chatbots in such a way that the whole theme of this engagement will be to drive the users away from these AI companions. But the current mental health apps in the market do not do that. They're trying to bring in more users to the app, so they are trying to influx more, not the so the outflux is not really their concern. And based on my research, I have concluded that people more and more engage towards the AI companionship apps. For example, if I am lonely, I will be more and more talking towards the AI companion app than I will be actually, putting the effort to talk to a real person. So I think the currently the application is increasing the loneliness than it's actually curing it. So that is why we should bring in the responsible AI and ethical frameworks to create these mental health care apps. So we should prioritize that the applications are engineered in such a way that they should be moving, the users should be moving away from these applications. So the whole theme should be in such a way that the user should move away from the application.
Okay, we are out of time for this particular presentation, so I am going to apologize to Bhupesh, who I know has had his hand up. But Bhupesh, can I encourage you to put your question into chat, and maybe I can invite Joel to respond in chat as well. In the meantime, it's time to hand over to Jashmin, who is going to talk about explainable AI models for prediction and interpretation of preterm births, please.
Yes, sir. Good morning, sir. So we basically studied on this explainable AI models for prediction and interpretation of preterm birth. Next slide. So first, one second. So basically, I would first concentrate here on what Elon Musk wants to quote. He basically wants to highlight the risk of AI's first development, advocating for regulatory oversight to mitigate potential changes or dangers, emphasizing the need for responsible AI frameworks. Next slide. So we would basically address all these three questions. The first question is, why is explainability and interpretability of models important? Well, explainability and interpretability in models are crucial for trust and transparency, enabling user to grasp decision-making processes and boosting confidence in the technology. And how does it help in achieving responsible AI system is basically they boost accountability by simplifying error and bias identification, ensuring regulatory compliance. They also allow users to question AI decisions and increase transparency, improving responsibility and human understandability in the technology. Then, where exactly our studies stand in this context is, as still now we understood that for a system to be responsible, it is needed to be explainable. We basically focusing on explainability as the first part or first step towards responsible AI. Next slide. So just a background, what is preterm birth? It's basically babies born alive before 37 weeks of gestation. What happens if the child is born preterm is it may lead to death of the infant, and according to statistics, some 9 lakh death in 2019, and many survivors who could live are basically facing disabilities like learning disabilities and visual and hearing impairment. So this is why early prediction of preterm delivery is very much crucial. Next. So this basically shows how it would help. It's basically need for early prediction of preterm delivery, where we could prevent severe health complications in infant, reduction in perinatal and neonatal mortality, timely medical intervention, and minimization of maternal health risk. Next. So basically, the objective here is the complexities of preterm deliveries necessitate early prediction. Just predicting preterm delivery is not enough. We should reason out why it is preterm delivery and exploring different XI models to explain all these predictions. And finally, focusing on simpler data. Here, simpler means computationally less expensive data. Those are EHR data like electronic health record to predict these preterm deliveries instead of any image or signal-based data. Next. So we have done a literature survey, and certainly these are the 4 papers that we have put here. So the first paper uses EHG recordings, electrohistogram recordings, and the authors have reported that random forest classifier proved to be predicting well. And then the second paper uses some images and use some multi-layer perceptron. A multi-layer perceptron outperforms with area under the curve 0.83. And further, they have used the third paper used some openly accessible data set and foster some artificial neural network and achieved a good ROC and specificity. Finally, paper that implement different classifiers and tried to explain this model prediction and using Lyman's trap. Next. So motivation behind our study is existing works mainly focuses on complex, costly to occur image like ultrasound and MRI, and signals data set that requires complex model implementation like CNN. And while aiming at increasing predictive accuracy, we lack the explainability part. We need to explain the decision why it is so and why it is not so. Next. So contribution here are we implemented various classifiers to predict preterm birth and added explainability on the top of it by implementing explainable AI models. Thereafter, we implemented this model on the CDC dataset, which is basically includes demographic informations and which is less expensive as compared to image and signal. Next.
Hi, my name is Krishna. I'm going to talk about our study. We use the open birth data from the Center of Disease Control and Prevention, CDC, USA. In 2022, out of 3.53 million births recorded in USA, 0.4 were preterm, 0.4 million were preterm deliveries and 3.13 million deliveries were normal, indicating around 11.62% deliveries are preterm, which is around 2 in 17 deliveries recorded. So it is observed that most of the Asian populations in US, excluding Filipinos, had a significant lower percentage of preterm deliveries, especially Korean and Chinese, with 8.2 and 8.3%, whereas the Pacific Islander and African American populations in the US had highest percentage of preterm deliveries, around 16%. Cesareans have a direct impact on preterm deliveries. It has reached to 50%, where the number of previous cesareans of a mother are 10. It is a very extreme case, but we can infer that if the mother had a cesarean previously, the preterm delivery likelihood increases. This is our system design, our methodology. We took the raw CDC text data and converted it to tabular format in pandas data frame. We cleaned the data, normalized, and we selected the features. And the data is visualized and analyzed as shown in previous slides. And we applied these 7 machine learning classifier algorithms. And the models are explained using LIME and SHAP. LIME is used to provide local explanations for a single instance. SHAP is used to provide global explanations, global feature importances for multiple instances, and the whole dataset. This is a single instance of our dataset, raw dataset. So the raw data is a list of strings separated by different lengths of spaces. If we use the user guide provided in the CDC website and pre-processed it, we have eliminated the rows with over 50% missing values, and the outliers are removed using Z-score standardization. Missing values are filled using mice iterative imputer. These are the 35 features that we have selected. The features include all categorical and numerical features. We first performed correlation analysis with the target feature, and then we handpicked 35 dominant features. These are the 7 machine learning algorithms that we have implemented. Overall, tree-based and boosting-based models achieve slightly better metrics. So this is a LIME output. This is a normal delivery test case explained using LIME. Here, blue indicates preterm and orange indicates normal delivery. These are the confidence of the model. And here, this table shows the feature data instance. This is the feature and this is the value. If we look at this data instance, the mother has gestational hypertension, had a previous preterm birth, used antibiotics, has gestational diabetes. So it is very possible to think and identify this as preterm delivery. But this is actually a normal delivery. We can see the features such as no steroids used and plurality. Plurality is the number of fetuses, no smoking, surviving children, no ruptured uterus, etc. And the decision learnt inferred by the model locally had a huge positive impact towards normal delivery. These are the local decisions learnt by the model. So in this case, we can infer that the mother took a lot of care in pregnancy and avoided the preterm delivery, even though there are lots of parameters like usage of antibiotics, diabetes, previous preterm birth, hypertension supporting preterm delivery. This is why explainability and interpretability are important. Unlike in some cases where it is very obvious to understand. For example, let's say the mother had more than one preterm delivery, smokes, had cesarean, has diabetes, then this is a almost certain case of preterm delivery. But in some cases, as this one, it is a normal delivery. So these are the cases where explainability of model predictions is more crucial. Here, this is a second test case showing preterm delivery Lyme explanation. Here, the mother does not have any complications like no previous preterm birth. Plurality is one. No gestational and pre-pregnancy hypertension. Did not use antibiotics. But still, it is a preterm delivery. As explained by Lyme, the mother smoked a lot in her pregnancy, and that has led to preterm delivery. As said before, SHAP, this is a summary plot displaying SHAP values for each feature, aimed at highlighting the impact of each feature has on the model output in the case of preterm delivery. The features are ranked according to the total magnitude of their SHAP values across the preterm samples. Steroids, plurality, BMI, these are the most dominant features in the preterm delivery cases. Here in our dataset, steroids is a categorical feature having the values 0 and 1. 0 if mother did not use any steroids and 1 if she had used them. we can see the impact it has when the value is 1, red color. The impact is very high, and it has a very minimal impact on the preterm delivery if it is 0, as we can see that on in blue. Here, gestational hypertension, antibiotics, number of previous cesareans, all these features have large impact towards preterm deliveries. But if we can see this red line here, prior terminations, this is very long. So what we can infer from this is prior termination strongly affects a small number of predictions, where features like gestational hypertension, antibiotics, and previous cesareans have a more moderate effect on all predictions. So in the samples where this prior terminations is influential, it has very strong effect than all those features. And there are many dependency plots of the features in the SHAP documentation. You can check those out. Jashmin.
So finally, we would conclude here that our study aims to predict preterm delivery through analysis of demographic information collected through EHR data. We use several classifier algorithms and boosting methods were implemented and analyzed. Lime model explain a local interpretation, and SHAP gives a global perspective. Results generated by Lime and SHAP model helps to understand and visualize the reason behind decisions made, offering a transparent view and giving an insight into the model. And thus, these explainable AI models offer interpretability, ensuring AI is used responsibly and reliably. Next. So in future, we would aim at exploring sophisticated deep learning techniques to boost the accuracy of prediction. There have been discoveries of vulnerabilities in both Lime and SHAP methods, indicating possible biases when subjected to adversarial attacks. Here, adversarial attacks means adversarial perturbations. We would further emphasize on testing models on various data sets for validation. We would also aim to explore the development of counterfactuals, which aims to reverse negative outcomes, providing strategies to prevent preterm delivery. Next. These are some of the references. Thank you.
Okay, my thanks to both speakers for that great presentation. There is a question in the chat from Karush via Daval, but given the time, and we are over time, I am going to move to the next speaker at this point. But if I can encourage Jashmin to have a look at the question from Karush in chat, please. I think that's quite an important one. However, in the meantime, I'd like to invite Pranav for the next talk, please, to share screen, entitled Enhancing Retinoblastoma Diagnosis, a comparative analysis of pre-processing techniques and transfer learning models with Lime interpretation. Pranav.
Thank you, Dr. Kumar. I'll share my screen. I request you to let me know if the screen is visible or not.
Yes, it's there. Over to you.
And I'm perfectly audible, right?
Yes.
Perfect. All right, so good morning, everyone. I am Pranav Sharma. I'm an undergrad student pursuing a dual major in biological sciences and electrical and electronics engineering at Birla Institute of Technology and Science, Pilani campus. Me, alongside my colleagues from Indira Gandhi Center for Atomic Research, have worked on enhancing retinoblastoma diagnosis. Now, this is a study of a comparative analysis of preprocessing techniques and transfer learning models with Lime interpretation. So I'll firstly begin with a brief overview of how the presentation is going to run down. So I'm going to start talking about what retinoblastoma is and how deep learning can be used for retinoblastoma diagnosis. Then I'm going to go over to the gaps, research gaps and the objectives that we found for this particular study, followed by the methodology results and the conclusions of the study. So what is retinoblastoma? Now, retinoblastoma is a rare form of eye cancer that primarily affects children. under the age of 2. It affects almost 1 in every 15,000 live births, and it can, lead to blindness or even cause death in some unfortunate cases. So particularly, it's a malignancy that is occurring in the base of the retina itself, and it's caused by a mutation in the RB gene, which is a tumor suppressor gene. So current diagnosis systems would firstly include, getting very minute symptoms from the children, such as leukorrhea or a squint or an ocular inflammation. But when you take the child to a doctor, the doctor might use bioimaging techniques like ultrasound, MRI, and CT scan to substantiate the presence of retinoblastoma. The current challenges in such a process is that there's a delay in the diagnosis. This is because of the fact that bioimaging techniques like MRI, CT scan, and ultrasound are expensive, and they're also limited in third world countries like India. So because of that, they're very expensive. The global south, particularly, is very inaccessible for this kind of diagnosis. Other than that, these bioimaging techniques may smaller and deep-seated tumors itself, which is why we propose the idea of using deep learning for expediting and having an earlier intervention into the diagnosis of the retinoblastoma cancer presence. What we aim to achieve is that the deep learning would be able to reach out to more people in an inexpensive manner, and we'll have better results from that. So the previous work that has been done on retinoblastoma diagnosis through transfer learning includes studies on inception V3, VGG16, VGG19, rest at 50, and exception. Other studies have included LPDMF method, multi-view CNN segmentations, and classifications. Beyond this, people have gone on to talk about Chappell line to understand the black box that is associated with the interpretability of the deep learning model itself. So firstly, we found some research gaps that were present in the literature survey that we did, which included that there's very limited scholarship on the preprocessing techniques in optimizing the performance for retinoblastoma diagnosis. The second was that there's a lack of study that correlated the Lyme explanations with the actual anatomical presence of malignancy in retinal images. So that's why we set out the objectives to be like that. The first objective was to implement a novel preprocessing pipeline and assess its effectivity on different kinds of training models that we were using. The second objective was to evaluate Lyme results on the pre-processed images and then correlate the models with the actual anatomical presence or the absence of malignancy. So we followed a 4-step method for our study itself. The first step was obviously data acquisition. We got it from an open source data sets that was present on GitHub. And the data set was quite even. It consisted of fundus images where 50.2% were labeled as benign and 49.8% were labeled as malignant. The second and the most important step for our pre-processing pipeline for our methodology was the image pre-processing pipeline. So the first step of this pre-processing included resizing, which helped us enable the images to become compatible with the model. So each model has a different kind of size that it can accommodate for understanding. The second was Gaussian blur. The Gaussian blur we used to particularly reduce the noise and any random pixel variation that could have been present at the time of clicking the picture itself. The third was normalization. Now, normalization is a very common technique that is used because it limits the pixel value to a certain range. And for the different kind of transfer learning models, different ranges are necessary. For example, inception V3 or exception for that matter only requires the pixel value to remain within a range of -1 to 1. The most important step was the dual tree complex wavelet transform, or DTCWT in short. What it does is that it actually enhances the image features. It conserves the edges and the contours. It's better with the tumor boundaries. And if you can compare the normalized image to the DTCWT image, you would see that the blood vessels are more highlighted and they're more prominent. And if there's a presence of microcalcification, which may indicate the presence of a tumor, it will not get it won't remain hidden and it will be very prominent. So that really helps us with the diagnosis itself. The transfer learning architectures that we used were, again, inception V3, rest 50, VGG16, VGG19, and exception. We used an ADAM optimizer 50 epochs with a batch size of 32 were used. Early stopping with the patients of 5 epochs was used to counter any kind of overfitting that might happen. Again, all of the training was done on ImageNet for all the transfer learning models. The matrix of evaluation for this study included accuracy, which is the proportion of correctly classified image to all the classifications that are done. And other metrics were your card index, which is the similarity between the predicted and the actual label. Dissimilarity coefficient, which gives us the overlap between the predicted label and the actual label. Other tools like explainable AI tools were also used. Now, what explainable AI does is that it makes the deep learning prediction interpretable. So broadly, if I tell you, the green areas in the images that you see show that there's a positive correlation with the prediction that is made. For example, the first image that is being done before Lyme and after Lyme was of a malignantly labeled image. So the green areas represent a positive correlation with the malignancy, and the red areas represent a negative correlation with the malignancy. Coming to the results that we got from the transfer learning model itself, the gray numbers represent the results from a previous study that was conducted in 2023 by some scientists in the US. We used these values as a base values and compared our results to them. The comparison was done because the gray numbers, the gray results were actually achieved through very minimal preprocessing, like pre-centering or resizing. And while we had used a very extensive format of preprocessing the images. So all the underlined scores in the right side, represented in white, highlight an improvement from the base values itself. So as you can see, Inception V3, VGG19 and Exception had better results from the previous studies when we used a novel preprocessing pipeline that was fabricated by us. So one problem that we might see, and you might see as well, is that Inception V3 had a testing accuracy of 1, a perfect score in the card index and DSE with 1 itself, and a very low testing loss. So this seemed very fishy to us at first. And when I talked to my supervisor about it, she started to laugh and she said, yeah, this was something that she was anticipating, given that the data set was just 281 images. So that's what got us to thinking how we can artificially increase the data set itself. This is why we got in data augmentation. So data augmentation also became a part of the image preprocessing itself. What data augmentation did was that it created artificial data by resizing or cropping or expanding the images in such a way that the diversity of the data itself increases. Because of the diversity increasing, the idea of overfitting also reduced. So basically, what our idea was that if Inception V3 is able to perform well on the augmented data as well, we would conclude that there's a substantial evidence for Inception V3 to be the best model for us. And that is exactly what happened. Even with augmented data, Inception V3 was able to give us very high accuracy. We got an accuracy of 0.9829, a testing loss of 0.0533, which is, by the way, 92% less than the study that was performed in 2023, a card index of 0.997, and a DSE of 0.9899. So overall, Inception V3 outperformed all the other models. Again, I would like to highlight that ResNet, in both the cases, was giving us very unsuitable results for retinoblastoma diagnosis. And this conversation is coherent with previous studies that have talked about the kind of results that they get from ResNet 50 and how it may not be suitable for retinoblastoma diagnosis. The final leg of our study included the usage of explainable AI tool Lyme, or the local interpretable model agnostic explanation, help us to validate the model performance by highlighting regions. So overall, when we used Lyme, we got two cases. Case A was more evidently present and case B was somewhat less present. So what case A is, basically the areas of high interest that are segmented with green were also the areas where the tumors lie. And the malignancy has been encircled in white, and you can see that almost all the time that they are lying over each other. While compared to case B, where the areas of high interest, represented in green, were nowhere near to the malignancy itself, and they were catching on to features in the background or irrelevant features, which points out to the fact that the the transfer learning model was catching on to irrelevant information, and it might be overfitting. With that, we drew the conclusions that Inception V3 outperformed all the other models. The proposed preprocessing pipeline did improve the performance of many models. Explainability was with Lime helped us to understand that and actually validate itself that the model's predictions were coherent with the anatomical presence of the malignant tumors itself. And some limitations were also noted by Lime that Lime's mislabeling some irrelevant information as being segments of as being segments for high interest. And with that, we propose that the future work could explore large data set, how to increase the data sets to mitigate overfitting, using tools like Smile for other explanations as well. With that, I thank you so much for your time. I hope you enjoyed the presentation.
Well, thank you so much for that, Pranav. We have time for questions, please. If you want to raise your hands or please type into chat, please go ahead. Okay, well, whilst we potentially wait for people to type, I'm really curious about how it latches on to the background there, Pranav. Do you have any explanations as to why it does that in some cases, but not all cases?
We try to explore it further why it catches on to the background itself, but currently we're not sure of what's happening. So me and my supervising are currently working on another project that's trying to understand it deeper. So we're using matrix to evaluate the explanation by explainable AI itself to actually get an understanding of how the latching onto the background itself is happening.
Okay,
So I hope we'll be down with some results and we can get back to you in a short period of time.
Yeah, that's great. We have a question in chat from Subramanyam who
Right.
asks why have we used Lime and not
Yeah, right. So why particularly I used Lime was that the previous study that we were comparing all our models to, we were taking the base case, keeping as the base case, also used Lime. So it really helped us substantiate that the pre-processing pipeline that we have followed has helped us to achieve better results. I would look forward to actually using SHAP as well and get an understanding of what SHAP has to say about retinoblastoma.
Fantastic. And the next question is, how can the decimal level metric improvements translate to, for example, a percentage improvement in diagnosis?
Right. So again, this was something that I also had some trouble understanding before, but looking at the literature review that we did, majority of the cases that have happened, especially because the data set is so limited, have pointed out to a very decimal change in improvement. So while it's not very strong, and I particularly would have liked number, to be in a whole number series, for example, 10% or like 5% even. This is something that people have gone on to say that, okay, it's better. We would try to actually, get some better understanding of how to improve it and get a better number in the future.
Okay, well, I think that just about takes us up to time. So my thanks
Perfect.
to you, Pranav, for all of that.
All right.
So at
Thank you
this
so
point,
much.
I will invite the next speaker, who is Temi, and Temi's going to be talking about a responsible AI perspective to implementing generative AI in personalized healthcare. Temi, over to you, please.
Thank you very much, Professor Kelvin. Can you see my screen, please?
Yeah, we can see that. Over to you. Thank you.
All right, thank you. Yeah, so I'll be talking about a responsible AI perspective to implementing generative AI in personalized healthcare. So we'll look at implications, challenges, and future direction. So this is basically a literature review of the implications of implementing generative AI in personalized healthcare, as well as the challenges and future directions. So my presentation outline is going to follow some few discussions around generative AI in healthcare, personalized healthcare, generalized AI in personalized healthcare, then some ethical implications of generalized AI in personalized healthcare, practical challenges, responsible AI frameworks, and we'll also look at recommendations for improving responsible AI frameworks. So I'll start by saying that key healthcare challenges, for example, include aging populations, workforce shortages, and as well as the growing demand for services. And these are seen to have overwhelmed the healthcare systems globally. For example, in England, as of July 2023, over 7.7 million people were always on the non-emergency waiting list, and we've got over 350,000 people who had been waiting for over a year. And so this has translated to each delay in accessing care. So there is currently each concerns around a number of institutions in England, for example, with respect to staff shortages. And this is what I think has brought more integration of generative AI into healthcare. So there are a number of use cases of generative AI in healthcare, from personalized patient treatment to chatbot for maybe patient management, medical examinations and training, to drug discoveries and development, to mental health support. And this set of use cases have seen tremendous growth in recent times. Our focus is basically around personalized healthcare. And so when we talked about personalized healthcare, personalized healthcare is concerned with tailoring medical treatment to individual genetic profiles, as well as their medical history. And so some of those advantages might include to minimize adverse effect, because the treatment are now tailored towards specific genetic expressions, as well as the medical history of the patient. And it's in a number of applications in pharmacogenomics, as well as in oncology, where cancer patients are being treated based on their personal genetic mutations, and so which leads to more effective and less toxic treatment. So basically, in terms of penetration, so generative AI in healthcare generally has the highest penetration in North America. So basically, US, Canada, and Mexico are the largest markets, and with around 40.2%. And then we've got the fastest growing market, which is Asia Pacific. We've got countries like China, Japan, India, and all others. So in terms of the market insight, generally global generative AI in healthcare are seeing over $800 million in 2022 in terms of investment. And it's projected that by 2032, we're going to have around $17.2 billion investment in generative AI coming from healthcare. So, and in personalized healthcare, which is the focus of this discussion in particular, the 2022 investment into generative AI in personalized healthcare runs to around $152 million, and is projected to grow to around $591 million by 2028. So this gives some sort of impression into the continuous penetration of generative AI in personalized healthcare, as well as more growing interest of people, stakeholders in in investing in personalized healthcare using with generative AI. However, there are a lot of major ethical implications with the leveraging generative AI in healthcare in general, and as well as personalized healthcare specifically. And because this is a literature review, so the details of some of these things can be found in the main paper, but I've just summarized the major ethical implications here. We've got algorithmic bias. We've got privacy and data security, as well as patient autonomy. So with respect to patient autonomy, for example, the AI recommendations may undermine patient autonomy and informed consent, because the data that goes into training the generative AI models may have come from some sort of data that did not pass through some sort of consent obtained from patients. And so patient doesn't really have a say to how their data is used and how their data is being integrated, as well as even when the model generates some result, they don't have an idea of how they could interpret the result, what happens before the results were actually obtained. And so one of the few things we found from some literatures in addressing ethical implications coming from generative AI in personalized healthcare include the introduction of diverse and representative data sets to train generative AI models. In terms of security, to inculcate robust encryption and secure storage in managing patient data and ensuring transparency. The place of introducing some sort of explainability, just like what the last speaker discussed, which could help to understand what the black box actually means, may also help to build, for example, the user trust, in this case, the patients. So there are key practical challenges in implementing some of these models, and some of such challenges include data quality, system integration. Always very difficult to merge generative AI models with existing healthcare IT systems, and sometimes they experience a lot of interoperability, and it's a little more difficult in terms of ease of use. So there's also the place of regulatory gaps, insufficient global regulations to govern generative AI in healthcare. I look at just two case studies here. There are a lot of case studies in the main article. So for example, when you're using GAN for medical image synthesis or for drug discovery based on the past clinical studies that have been conducted, which we reviewed, some considerations include bias detection and transparency. So we identified that limitations around GAN being used in these application areas include, it includes that GAN has to be trained with diverse data set to avoid bias, because GAN is prone to biased outputs. It also has issues with privacy. So it's important that we ensure that synthetic data is not identifiable, or when there's a reverse engineering that does not reverse back to the real patient data. Then the issue of transparency, it's also recommended that GAN models should be interpretable for healthcare professionals. So we should ensure we introduce some sort of interpretability into the into a GAN model if you'll be using that. For variational autoencoders, so the focus is basically around integrity, explainability, and fairness. Those are the weaknesses that have been identified with variational autoencoders, and that was when it was used in applications, for example, in anomaly detection, medical imaging. And so some of the recommendations includes that for variational autoencoders to be interpretable, we need to ensure that we include some interpretable models in the integrated together with variational autoencoders to make them more interpretable. In terms of fairness too, we need to avoid potential bias, because it's prone to skill training data, and that could lead to misrepresenting some underrepresented classes or categories in the data. So so the key few responsible AI frameworks, and so for example, the EU AI Act 2024, which focuses on AI transparency and regulation. And so one of their focus is basically transparency and regulation, and they also emphasize the need for human in the loop approach for safer clinical decisions. So it is important that frameworks that responsible AI frameworks be adaptable to healthcare in a way that requires continuous monitoring so that we can manage bias. There's also a need to ensure that the decisions that are made by these models are transparent and explainable to clinicians and patients. So our study recommends a place of interdisciplinary collaboration or cross-institutional collaborations, co-designs, where we also develop the model alongside with the patient or the end users that be making use of the application, improve data governance, as well as transparency and accountability, as I mentioned before. And then in the process of the design, while you conceptualizing even the development of the model, there must be ethical AI design. I mean, responsible AI frameworks integrated into the model. So I will conclude by saying that future directions should focus on in-house generative AI solutions that are developed and deployed locally to address data privacy issues, and then tailor policy regulations and responsible generative AI framework in personalized healthcare. So I'll just leave with this thought. Excitement for precision medicine must be matched with clear-eyed examinations of the possibility for this emerging field to exacerbate existing risks or create new points of vulnerability. That's a note by Khadija and Michaela. So these are some references, and thank you for listening to me. If you've got questions, I'm happy to answer. Thank you.
Okay, thank you very much, Tammy. We have time for questions. And again, if participants want to type in chat or raise their hands, very welcome to do so. Well, I think I'll kick off the questions since I can't see any there, Tammy. My question relates to the first part of your talk where you were talking about market penetration. I was curious why, in your opinion, most of the market penetration is happening in North America and the Asia Pacific. I'm really curious, why not Africa or Europe?
Yeah, well, I would say that largest market basically right now is US, Canada, Mexico. Most of the big techs are actually located in this environment, and so there's a strong competition in terms of who takes the lead in generative AI and the different diverse applications, especially in healthcare. And so the companies like Google, companies like Microsoft, and all of that have most of their offices located, the main offices located in the largest market areas. That is North America, US basically, and then you have some of them too in Canada. So from there, they intend to reach out to other parts of, and you can see that the reason why you see the fastest growing market to be the Asia Pacific is because there's a strong competition between US, for example, and China. And so at some point, I don't know, I don't want to talk about COVID-19 anyways because of a lot of things, but there are a lot of speculations around how COVID-19 came. Perhaps it was a biological weapon manufactured by XYZ. So there's this strong conflict between US, China, for example, and so they always want to match up with development in that context. So I think that's my opinion.
Okay, thank you very much. I'm going to bring Karush in there, please.
Thank you, Kevin. I just try to, let's say, have the question very quickly. So you talked about fairness and explainability. So, and we had some presentation about methods like LIME and CHAP, but given the kind of, let's say, the growth rate of generative AI and let's say models like transformers and large language models, there is a challenge that how we can explain the behavior of, let's say, something like a large language model or generative, let's say, models for, let's say, generating some images or something else. So do you have any, let's say, thought on that how we could use the existing models like LIME and CHAT on these huge models, generative models in AI? So I would appreciate your, let's say, comment about that.
And if I can encourage a brief response, please, in the interest of time.
Okay, all right. So thank you very much. I think basically, so um, it starts with understanding, for example, use cases. So set up use cases and then have written explanations of how generative AI could be applied in that context. And then we could look at how, for example, Sharp or Lime perhaps in the past generate some sort of recommendations to or some explanations in this same kind of line of case studies. And then we can look at how humans will be able to explain such explanations, because that part where it's the interpretability, for example, is, I think, is the part you are trying to strike on. If I look at what Lime or Sharp has given to me, am I able to understand that explanation very well, and does it correlate with what I really need? And so I think the most important thing is not just to talk about fairness, but we should also talk about fairness with respect to interpretability. Do we make does the explanations provided by the model um, making sense to me, and is it the same kind of explanation I would give as humans? So I think there should be some sort of training data set of explanations given by humans and explanations given by models, and find a way to penalize, develop models that could penalize where the explanations by agents are not too close to explanations by humans.
Okay, thank you.
Thank you.
Tammy, there's also a question in chat, but we are going to have to move on at this point. So I'm going to invite Maneeha to present on Neuro Symbolic AI and large language models, a survey. Maneeha, please.
Thank you, Dr. Kevin. I am Maneeha Rani, and I'm a PhD student at Center of Excellence for Data Science and Artificial Intelligence and Modeling at University of Hull. So I would be presenting today a survey paper titled Neurosymbolic AI for Explainability in Healthcare. The authors include, apart from me, the authors include Dr. Bhupesh, Dr. Dhaval, and Dr. Bill Jones. So basically, this is an LLM application. There are lots of applications in healthcare for both medical professionals and for both patients, but still, LLMs in healthcare are struggling with lots of challenges. The challenges which I have been through in my literature review that include trustworthiness, explainability, biases, and fairness. For this paper, I have targeted more explainability. There are lots of solutions which can be proposed to make a model more explainable or more reason-oriented, but neurosymbolic AI is one of the solution for it. So neurosymbolic AI can be used to make the LLM more interpretable and explainable. Overall objectives include to explore neurosymbolic AI for improving interpretability and explainability, primarily through the symbolic component. Apart from this, my objective was to propose symbolic AI integration with LLMs to enhance explainability, and it further includes the introduction of various integration stages for symbolic AI and LLMs, and then to present the state-of-art achievements and challenges. So, what exactly the neurosymbolic AI is? Neurosymbolic AI is basically an integration of symbolic AI with neural networks. Now, symbolic AI can be in various forms. It can be a rule engine, a knowledge graph, or symbolic logic. So when integrated symbolic AI with neural networks, we can make neural networks more reason-oriented and more explainable. If we talk about the approaches which are with the neurosymbolic AI, with respect to the interaction level between the symbolic component and the neural component, they're categorized into two parts. First is sequential, and the second one is hybrid. In sequential component, neural and symbolic parts both are working in a series, and they are usually loosely coupled, and they are dependent on each other, but not very much. They can work independently. In case of hybrid approaches, neural component and symbolic component both are nested together, but again they are loosely coupled. In case of cooperative, they work independently, like symbolic component is working independently to that of neural component, but they are depending on each other for their outputs. For example, sometimes the symbolic component is working and is presenting certain output to the neural component for processing it further. So they are also loosely coupled. In case of compile, usually the symbolic components, lots of symbolic component or single symbolic component is coupled or tightly coupled within the neural component. Same applies to the other part. For example, symbolic component will be embedded within the neural component and it would be tightly embedded. So this is the approach's categorization with respect to the level of interaction they have. In literature, lots of frameworks have been proposed for neurosymbolic AI. I would be discussing those frameworks just briefly, not in very much detail, but those frameworks are mainly emerged from the categories that include high reasoning and low learning system. That means some of the system would be more oriented towards the reasoning, but not that oriented towards the learning. That simply means that LLM contribution or neural part contribution would be relatively lesser than the other component. And the other categorization is low reasoning and high learning system. That includes, they were pretty much low in reasoning but high in learning. So neural contribution would be more in those components. Lots of approaches are being used for each of these categories, so I won't be going in very much detail. Instead, I would prefer to discuss the architecture of popular frameworks. Some of the popular frameworks which are being used for neural symbolic component include logic tensor network, neural logic machine, TensorLog, neural theorem provers, and deep problogs. So they have different architecture. Each of them is different with respect to architecture, with respect to the syntax they are using, and with respect to the application in which they would be deployed. In case of most of these components, they are using relational system and sometimes first order logic. But again, the syntax, if it is using first order logic, it is possible to use any other syntax as well. For example, they can use that schema sometimes, and they can use. So basically, the purpose is in popular frameworks, maths is basically incorporated in order to enhance reasoning further. So this table has lots of details here. In case if you would like to ask any question, I would appreciate, but if I be in more detail, I would be short of time. So let's just move forward to the next slide. Strengths and weaknesses of symbolic AI and LLMs. So perhaps at this point, I was interested in integrating neurosymbolic components with large language models. But if I go into the literature, there are very few approaches which are actually discussing the algorithmic perspective or implementation perspective of neurosymbolic AI with large language models. So most of the approaches in the literature are targeting neurosymbolic integration with LLMs, but only either the theoretical perspective or they are using they are using large language models to enhance neurosymbolic component. So I could not find lots of approaches or lots of literature which were integrating neurosymbolic frameworks with large language models. So I found a direction in which I wanted to integrate symbolic AI with LLMs, considering the benefits that symbolic AI provides to the neurosymbolic component. So symbolic AI generally is very good in terms of reasoning. They provide very high level of explainability. But if we talk about LLMs, they're very good in language generation, but may not reach up to a certain level to provide explainability. So in case if we integrate symbolic AI with LLMs, considering the reasoning from symbolic AI and learning from LLMs, I think it would provide a better solution towards the reasoning and explainability of LLMs. So the solution is now to provide LLM integration with symbolic AI. Symbolic AI can be in the form of knowledge graph or it can be symbolic logic. It can be in many other forms, but I have not discussed that component. At the moment, I'm focusing knowledge graphs and symbolic part only. So when integrated symbolic AI with LLMs, it can be integrated at various stages of LLM. For example, it can be integrated at pre-training, it can be integrated at inference stage, or it can be integrated at post training or fine tuning. So in my literature, what I have done is I have divided the symbolic components in two parts, and then I've considered various stages of large language models, and I've tried to incorporate all of these symbolic components with LLM in different stages, and then through the literature, I have found certain existing approaches and then categorized according to the stages of LLM. And then my major aim was to introduce what are the state of art achievements in this field and what are the challenges, so how we can improve them. So basically, this is a slide which represents the integration at different levels and state of art achievements and challenges as well. So symbolic AI is integrated with LLMs. Now, symbolic component can be in the form of knowledge graph or it can be in the form of logic rules. So knowledge graph, when integrated with LLMs, it can be integrated at pre-training stage, it can be integrated at training phase, it can be integrated at inference phase or post-training phase. So various approaches which are used to integrate knowledge graph with LLMs at pre-staining stage include embeddings, word mask optimization, conversion of textual input into the trees. In training phase, they might include knowledge-infused self-attention transformers, focus fusion attention mechanisms, dual interleaved attention mechanism, additional adapters, as well as specific encoders. Inference stage, it might include RAG. Most of the approaches are targeting RAG these days when they try to incorporate knowledge graphs in LLM, and the reason is it provides more accuracy. In case of post training, further further literature is needed to validate the content. And the purpose of incorporating symbolic component in post training is to validate the content through accuracy. Concept nets and knowledge based prompts are also used here. Now, if I come to the next part of it, that is logic rules integration with LLMs, this includes various rules at various stages. For example, for pre-training stage, logic rules infusions with training data for structured logic patterns and logical constructs, embeddings, symbolic data augmentation, and logic guided model vocabulary are some of the approaches which are very common for embedding logic rules into the pre-training stage. If I talk about more common and more viewed literature in fine tuning, it includes logical rules, propositional logic, first order logic corpus for fine tuning without altering the architecture. And at inference stage, external symbolic solvers are incorporated into the symbolic pipeline or inference pipeline for reasoning. Sometimes in logic oriented integration with LLMs, what is more common is to enhance the logical component instead of enhancing the LLM integration. So specifically, those approaches are discarded which were enhancing logical component instead of LLM integration. So now is the time to discuss state of art achievements. So in literature, most of the times, RAG, PEFT, and KG adapters are considered as state of art achievements, but still they are struggling in terms of accuracy, scalability, and interpretability. Apart from this, is knowledge validation by using hybrid approaches is also considered a state of art achievement. If I talk about the challenges, current challenges that it faces include conflict resolution. So, conflict resolution refers to sometimes the symbolic component comes up with another retrieved answer, whereas LLM comes from another retrieved answer. So, it becomes very difficult to resolve the conflict. And there are certain algorithms which are used to resolve the conflict. There are certain algorithms which are used for this purpose, but further research is necessary, and it is considered as one of the challenge to resolve the conflict between two modules. Apart from this, it includes to develop different mechanisms for integrating real-time updates from knowledge graphs. So knowledge graphs can be static or they can be dynamic. These days, property graphs and dynamic knowledge graphs are getting more in trend. But to develop the mechanisms which can integrate the real-time updates from dynamic knowledge graphs is still considered as a challenge. Apart from this, one of the challenge includes to integrate structured reasoning paths without compromising performance. So usually when the reasoning paths or reasoning scenarios are incorporated, the major challenge faced here includes the performance. So performance is usually compromised. There are lots of solutions which are proposed to adjust this performance area, but still it is lacking. Apart from this is one more complication that includes computational resources. So model complications and computational resources addressing is considered a challenge in order to effectively incorporate symbolic component in LLMs. But all of these achievements that I have discussed are usually focusing knowledge graphs. If I talk about logic rules are having certain state-of-art achievements in pre-training stage. But if I talk about during the training stage, specifically targeting the architecture of transformers mechanisms and knowledge-infused attention mechanisms, it's still lacking in terms of literature here. Now, the sole purpose was to enhance explainability at different levels. Now, explainability factors can be reasoning, it can be a trust, it can be reliability, robustness, safety, and security. Now, explainability can be at data level, it can be at model level, or it can be at inference level. So when LLM integrated with the symbolic AI, the next aim was to go through various literature studies which are being used to enhance explainability. It can be any factor of explainability, but the goal should be to use symbolic AI integration with LLMs to enhance the explainability at any level. It can be data level or model level or inference level. So the paper provides a detailed comparative analysis of approaches which target explainability at different levels. I've just included a table here, a brief comparative analysis of what is presented in the paper. I won't be going into the much details. So to conclude, this survey paper discusses various challenges in LLMs and then discusses various possible solutions, and discusses neurosymbolic AI as one of the solution. Apart from this, neurosymbolic AI frameworks and approaches are presented here. Then, since in neurosymbolic AI, the reasoning is usually because of the symbolic component. So direction here is to embed symbolic component with LLMs and then to go to the comparative analysis of existing approaches which are using symbolic integration with LLMs to target explainability. In last part of my paper, I have explored state-of-art achievements and challenges in integrating symbolic components, such as knowledge graphs and logic-based reasoning at various stages of LLM lifecycle, including pre-training, inference, and fine-tuning. So thank you very much for listening to my presentation.
Okay,
That's
thank
all.
you very much. And in the interest of time, we are going to move on. If there are any questions for Maneeha, please type them into the chat. But on behalf of all the organisers, I'd like to thank all the speakers from earlier this morning. Thank you so much. And I will hand over to Dhaval as the next chair. Thank you very much, everyone.